Alright, sorry for that long introduction of nothing. So now we're just going to evaluate the line integral where our curve is the given curve. So we're given our function again at f of xy is z, so it's really giving us the height of whatever surface that 10 minus 2x minus 5y is given us. And so what we're going to do is we're going to evaluate the line integral. All right, so what we're doing is we're just kind of just cutting a slice of our surface, and we're trying to find the area underneath that small little slice. And so we're given our functions already in parametric form. X equals t, and 2 minus t is y, and we're told that we're going from 0 to 2 on our line integral. So I went ahead and put it into our formula. So we're doing the integral from 0 to 2 of our function, and I'm going to substitute in for x, t, and then for y, 2 minus t, into the function. The square root of the partial of x with respect to t is going to be 1. The partial derivative of y with respect to t is going to be -1. Square both of those, you're going to get 2. I pulled the square root of 2 outside. The integral from 0 to 2, went ahead and combined like terms. 10 minus 2t minus 10, so 10 minus 10 goes away, minus 2t plus 5t is just 3t. Integrate the 3t, and when I integrate the 3t, I'm going to get 3 over 2 times t squared from 0 to 2, and then, of course, have the square root on the outside. 6 minus 0, square root of 2, 6 square roots of 2, that's the final answer. All right, so again, something that's not very difficult. Again, you can pause at any time to solve for this. But again, something that's not very difficult to do. You just need to make sure that you plug in. And there are going to be times where you have to reparameterize the function yourself. And so if you recall from very early in the beginning of the year, we talked about parameterizing line segments. And so here you have just a brief like a recall of how to if we want to do parametric equations with x and y, we can just take the line segments. And so from the 2 points, there's the first point, there's the second point of x, and then y. All right, and then again, this is going to be from 0 to 1 for time. So for time between 0 and 1, this is how far we're going to go. All right, so example 2. Evaluate the line integral where c is the given curve, x sine of y ds. C is the line segment from 0 to 3 and to 4 to 6. And so we're going to go ahead and reparameterize x and y. And so we're just substituting in our values. So initial x is 0. X of 1 is 4. Go ahead and plug that in. We're going to get 4t for x. For y, we plug in 3 and 6. We're going to get 3 plus 3t. And of course, this is going to be between 0 to 1 for t. All right, and so now we go ahead and plug this in to our line integral formula. And so x is going to be 4t, so that's 4t. Sine of y, I'm just going to use my shadows to point. Sine of y is sine of 3 plus 3t. And then the square root of, so again, our distance or our arc length is going to be the square root of 4 squared plus 3 squared, which is going to give us 5. And so I can pull out the 5 with the 20 on the outside, and I'm just left with t sine of 3 plus 3t dt. Now I'm going to go ahead and integrate. The good thing about this is when I do this, I'm going to do integration by parts. So what I did was the tic-tac-toe method. Is that what y'all call it here? I don't remember what y'all call it here, but so I went ahead and took the derivatives of t and integrated sine. And when I do that, take the cross products of both of those, and so I'm left with -1/3 t cosine 3 plus 3t plus 1/9 sine of 3 plus 3t from 0 to 1. Plug in the 1, I get -1/3 cosine 6 plus 1/9 sine of 6. Plug in 0, I get 0 for the cosine. part, and then I get negative 1 9 sine 3, and that basically stays the same. I can pull a 9 out, which I did. That way I don't have any fractions on the inside of my parentheses. And there's the integration. Now, recall, and this is a major part of, while we do line integrals, is we can find the center of mass of the wire with density function rho is located at the point x bar, y bar. And again, now this is messed up. It's supposed to be x bar is equal to 1 over m, the integral m rho xy ds. Y bar is y bar here. And then the mass density function is just going to be given by the integral of our curve rho xy ds. So again, when you're doing x bar, you're putting in another x inside your integral. When you're doing y bar, you put another y, and making sure that you divide by the total mass. And again, in order to find the mass density function, you have to have rho. Now, in order to find the mass, you have to have the mass density function, which is rho. All right, and this is a huge application of line integrals.